Okay, let's continue. So we had proven the last time this proposition, which was an immediate consequence of this valence formula, which stated that the sum over the zeros with an appropriate multiplicity equals k over 12. And it's maybe too loud, it's over. Okay, let's see whether it's better now. So we had this formula, and out of this corollary or this proposition, we can deduce the dimension of the space of modular forms. So essentially, it is just the multiplicity of 12 plus 1, but there's always something going on in weight 12 plus if k is congruent to 2 mod 12. And so on the last line, I've displayed this sequence of numbers. And so it's a very famous sequence. And if you go to OIs, which I really recommend, so it's the online encyclopedia of integer sequence, where you can find for any nice sequence, you find a description where it occurred, what is the generating series, and what is the references. You can look for more information on this. And this sequence is so important that it's also in there. Okay, so now we have this space of modular forms. We know the dimensions. And now we want to see what does it tells us. So I started with saying having modular forms gives you identities, because usually you have more ways to write these modular forms. For example, in weight 8, you have just a one-dimensional space, but you have the square of E4, and you have E8, and therefore there must be multiples of each other. It's a one-dimensional vector space, therefore you just have to compare the first coefficient in the Fourier expansion. If this coincides, all the others do coincide, and this gives you the so-called Hurwitz identity we had seen before, expressing the 7th power divisor sum in terms of this convolution of this power divisor sum of degree 3. Another identity we get just by free is this very nice expression for this delta function. So this delta function, again, is in a one-dimensional space of cusp forms. And we know that E4 to the cube minus E6 to the squared has a non-vanishing constant Fourier coefficient. And now we look at the first coefficient, then it turns out that this is 1728. And therefore, this series starts with Q. And therefore, it has to be delta, because delta was going with Q product, this 1 minus Q to the n to the power 24. Okay, so we get these identities for free. And now we want to see what is a vector space for this space of modular forms. And then it's easy to see, and I will be quick in the proof because I was 15 minutes less the last talk, and I will put this on the web page again, and so you can just read off. So the idea is simple. If you have a relation with a constant term, then you can plug the 0 of the constant term, and then you get a new identity, and then you divide out, and then you get something that it's impossible. Okay, and In particular, this can be done algorithmically. So if you have a modular form, then if it has a constant term, you can add some multiple of the appropriate power of E4 and E6. Then you get a cusp form. If you have a cusp form, it must be divisible by delta. And you are in the next step of the algorithm. You have a modular form. Then it's either a cusp form, or if it's not a cusp form, you can subtract a multiple of this monomial in E4 and E6. And you can continue, and at the end, you are landing in a polynomial in E4 and E6. Okay, and the next is, it could happen that E4 and E6 would satisfy an algebraic relation. But combining together what we have seen before, namely that the monomials in E4 and E6 do generate the vector space Mk, we see there's no linear relation in between them. And at the very beginning, we have proven that there's no relation between modular forms of different weights, and therefore there is no possibility for a polynomial which is non-trivial to hold for this E4 and E6. And so we have finished with the first theorem I wanted to present you, namely, we have this ring of modular forms. Maybe because it's important, I write theorem for this. So that the ring of modular forms is a graded polynomial ring which is generated by these two modular forms E4 and E6. And by abstract algebra, this is just a polynomial ring in two independent variables. A side remark for the experts. We have now the generators in two different degrees. So one is weight 4, the other is weight 6. And this is due to the fact that if you look more closely to this modular curve, then it's not an algebraic curve, it's more what people call an algebraic stack. And this is due to the fact that this action of the stabilizer of I and the stabilizer of this omega is not the trivial group, it's just this action by a group of order -2 and -1. And this is a fact that there can't be a nice moduli space of elliptic curves. And you see this in this weights 4 and 6. And if you take a higher level, then you really get rid of these problems. So you really see some very deep arithmetic problems already in this very simple formula here. And this is a side remark. But okay. There was also a subject I wanted to cover the last time as a kind of supplementary stuff. So if you have a modular form, then you could ask for its derivatives. It turns out that the derivative of a modular form is not a modular form anymore, because it has then a more complicated functional equation. So there's an additional term popping up. And this additional term is not too bad in the sense it is reproducing your function and it's just having this additional factor in front. And so it's just the usual formula of making the derivative of a composition of function, which gives you this equation. And now we have seen this kind of functional equation before, namely the Eisenstein series of weight 2, which we defined as being this Q series. We have seen that it does not satisfy this modular transformation property, but almost. And then if you use this, you can show that the so-called Serre derivative will be a map on the space of modular forms. And so again, this can be seen in a higher context of Gauss-Manin connections and so on. So you have an additional structure on this space of modular forms by having these various kinds of derivative. It can be put in a even more complicated setup, but for us it's enough to know that we have this map. And now we can make the ring of so-called quasi-modular forms, which is then the ring generated by this Eisenstein series of weight 2 plus the ones of weight 4 and weight 6. And we just make a polynomial ring out of these. And the point is that this is closed under the usual differentiation. And this is seen by just proving the identities that you give the derivative of E2, E4, and E6. And in Ramanujan notation, this is called PQ and R. And so in my work, this ring of quasi-modular form naturally occurs. And also my algebra is closed under this differentiation. And therefore, I just wanted to tell you that there's this result. Okay, so this was a very quick recall what I wanted to do the last lecture, and actually it took me 9 minutes. So if you make this, d tau, this is essentially q dq, and now I have to be, I think it's 2 pi to this direction. Okay, so there's a longer story on this space of quasi-modular forms. So you can embed this in various spaces. So in the spaces of various cross conditions towards the boundary, you have this quasi-modular form. You have, what's the name? Nearly holomorphic forms. And all these spaces are similar. And for us, it's just important. If you make the ordinary derivative of a modular form, then you won't get a modular form. And later we will see if you make the ordinary integration along a line, you will get something which is also not modular anymore. But this will give you some interesting numbers which are related to periods. So this is a story you have to know. And there's a full chapter on these quasi-modular forms and nearly holomorphic forms and so on in these notes by Zaki. And you have these famous identities of Ramanujan, and this can be put also in the context of Gauss-Manin connection on the modular space of elliptic curves. And this is the only thing I want to tell at this moment, because this was the last talk, and now this, the idea for the second talk was to discuss on modular forms and the L series, and why people want to study the L series attached to modular forms, because they have very nice aspects. We have seen things of this in the last day. The keywords are motivic or automorphic, cuspidal, and so on. And what we want to do is just to go to the very basic concepts. We want to see these L series have a region of convergence, they have analytic continuation, and they have a functional equation. And later we will see that the special values of these L series have some nice arithmetic information. So these are just very few points. We will see a little bit about this, how you call this, we've seen yesterday in this tensor product of representation, which is just a convolution of L series which comes by the so-called Rankin-Selberg method, which can be seen by what is the keyword was parabolic induction, which can be put down to earth. This is what we want to see today. And the first is, if you want to make L series, you want to discuss about the region of convergence. And usually you prove the convergence by comparing it to the Riemann-Zeta function. And therefore, if you know that your coefficients satisfy some polynomial growth then this gives you very quick proof that you have convergence in some half plane. And in particular, if we have an Eisenstein series, then we have constants A and B, such that the growth of the coefficient is bounded by the n to the k minus 1 power of an above and below. And what to do? It's like we look at this, and now we just have to bound this divisor function, and obviously the divisor function is summing up over all divisors, and we just take the biggest one, then it is clearly smaller or equal than the sum over all divisors of power divisors. And in the other direction, we just expand this, and then we know, because D is a divisor of n, we could put it, we can put it downstairs, and instead of summing up to n, and only the numbers that divide to n, we can just add over all. So it's a very rough bound, and then we get this upper bound. So this is down to earth and very easy. And now the next is, if we have a cusp form, then we can bound the growth of the coefficient by n to the k half, where k is the weight of this modular form. So how to prove such kind of result? So we look at the nth coefficient, which can be obtained just by getting rid of the periodic part. So we just have to multiply with the right frequency, and therefore we get this formula for the nth coefficient. And now this means that the nth coefficient can be bounded by the supremum of this absolute value of f of x plus I tau. And now the idea is we consider a bigger quantity, namely the norm of f. So this is somehow what I consider as the pointwise Peterson norm. So we had seen yesterday the Peterson scalar product. In the Peterson scalar product, you have this Peterson product, which is actually defined as being a pointwise invariant metric on your vector bundle. And then you take the L2 norm of this metric, which is then called the Peterson norm or Peterson metric. So you have this quantity, which is invariant under SL2Z, but now you have a cusp form. This means that your norm is invariant under the group, but as you have a cusp form, you will see on the next slide that if you go to the boundary, then this norm will go to 0. And now we are on this fundamental domain, and if we go to the infinite, then it will be 0, and we cannot go too low, and therefore this norm will be bounded in this domain, and we get this constant here. So we get that the Peterson norm is bounded on this domain, and now we put it on the other side. We're just resolving for the quantity we wanted to study, and now we get this bound here. Okay, we recall that we started with this inequality. This holds for all y, and so we just take y to be 1 over n, and so we get what is called as the Hecky bound. Okay, so we've seen that the coefficients of these modular forms are bounded, and depending on whether it's a cusp form or not, the bounds are different. And actually the story is far from being optimal, because if you apply some deep results of Deligne, namely his proof of Weil conjectures, to the q-Zeta variety, to the products of elliptic, so it's fibers of products of elliptic curves, then you can apply there some cohomology theory, you can calculate the trace of Frobenius and so on, and then this gives you the L factors of the modular form, which must then be a Hecky Eigenform, but then you get a much, much stronger result. And so then actually this is even better? Okay, maybe who's the expert? Is it the right one or is it even, I think, is this the correct bound or is it even the better? I think this one. That's the right one. Okay, so you get this. You get this bound, which is much better. And so it is just, again, as an indication, you have several layers of difficulties. And so you started with Eisenstein. This was almost trivial. You have to cast form. You have to have a little bit of concept of invariant norm. And if you go even further, you get much better results. Okay. And now we come. Yeah. Okay. Working so long with modular forms, I would. Okay, so working long enough with modular forms, I would just say yes. So every quantity that has a nice definition with modular has some meaning. And actually, the meaning of this, it is a subnorm of this. And actually, the point is, this is the has to do with the Faltings-height. So the Faltings-height is essentially given by this Peterson norm of these modular forms, and therefore you have a sub of a kind of Faltings-height, and this gives you a kind of information. And I would expect it would be at CM points and so on, but I'm not aware about concrete conjectures about this. But I think the question is natural. I would expect this is a kind of special point in the fundamental domain, giving you this maximum. Of course, you should not take an arbitrary modular form. You should take a Hecky Eigenform in order to get some nice results, and maybe you have to take the average over all translates of the Hecky algebra or something like that. But of course, everything with modular forms which is special has some special meaning. That's my philosophical answer. And okay, and I expect it has to do with Faltings-height of abelian or varieties. Okay, let's come back to this L series. So if you have a sequence, then you can make an L series just by dividing the nth object of your sequence by n to the s, where s is some complex number, and then you can sum this up. And the point is, if you have a modular form, then this series is convergent to a holomorphic function just of your complex plane, and it will be there. Oops, sorry. And it will be a holomorphic function there. And the miracle is that you can extend this holomorphically to the whole complex plane. And moreover, you have a functional equation relating k minus s and s. So if you know the value of the function here, then you know it on the other side also. And there's a, yeah, okay. And if you just take an average arbitrary sequence, you won't have such a nice domain of convergence. And by no way you would have analytic continuation. And it's even more unlikely to have a functional equation. So it's among all integer sequence, this is a very strong property. And how to prove this? So the first one is quite easy. As I told you before, you just take these bounds for the coefficients, and then you compare it to the Riemann zeta function, and it is well known that the Riemann zeta function is convergent right to the real part of s equals 1. Okay, so this is the easy. The other one is a little bit of analytic number theory. For this, you need to know the following two basic objects. So the one is that you have an integral representation for the gamma function, and the other one is somehow the key in this Mellin transform business, that you can express the n to the minus s as being the product of these prefactors and the exponential integral for this. And now you just plug it into your series. So this is the definition. And now we replace this n to the s by this object here. And then we come up by, okay, then we have to say a little bit why we can interchange summation and integration. And essentially, if you look in these older textbooks of complex analysis or even analysis, it is just made in such a way that we can do this at these points here. So it's really the conditions you learn in analysis when you can interchange summation and integration. Is just handled in such a way that this works here. And then if you do this, you end up that you get nothing else than the modular form in evaluate at IT. And the story here on this slide is also known as the keyword. This is nothing else than the Mellin transform, that the LCS is the Mellin transform of the modular form. But now we can continue further, and for this we split this integral from 0 to 1 and from 1 to infinite. Then we make a change of variables. So because in 0 we don't want to integrate because we don't know exactly what is going on with our modular form. And so we make this substitution, and then again I make a heart because now the modularity is playing a role, because now we can change this expression here by using the modularity property of f, which is in particular holding for this choice of oh, sorry, there's a typo. For this choice of tau. And now we have this more beautiful integral, and now we see everything is holomorphic. So the modular form is holomorphic for this I tau, and this epsilon is, I'm sorry, we ask for holomorphicity in this S. So this term has no problems in holomorphicity of F, and therefore we did get this holomorphic continuation. And furthermore, if we replace S and K minus S, we get this functional equation, and so we get the claim. Okay, so again, we see doing this straightforward calculation, which is not difficult to justify. We get that the L series has these nice properties, and we just remind you that the functional equation has to do with the modular transformation, and even you have a converse theorem of Weil. It's roughly saying if you have an L series with a functional equation of type as we've seen before, maybe we should let us say this is some gamma factor, so it's some powers of pi and so on, I won't specify, then it has to come as the LCS of a modular form as soon as you prove some additional analytic datum, which is grows on vertical strips. And again, the prototype of an LCS with functional equation is the Riemann-Zeta function. And actually, this is proven by using the modularity property for the theta function. Okay, so you have these nice LCS. And the point is that if you have an LCS, you think of Riemann-Zeta function. And I hope everybody knows that the Riemann-Zeta function has this Euler product. And you can prove this just by multiply this out and using this geometric series expansion. And so the natural question is, which of these L series attached to modular forms have an Euler product? By this we mean that we want to have that the L series can be written as a product over these local L factors. And again, a side remark, yesterday we've seen Zischer working on these local representations, and these local representations are just giving you these local Euler factors. So from the local data, from this local representation, you get the data that is needed for this local Euler factor. And okay. And the answer to this question is that Hecky Eigen Forms will precisely give you the LCS which have this Euler product. And so this is my motivation why we want to study Hecky operators. And for us, a Hecky operator will be just a manipulation of this modular form, namely the manipulation given by making a weighted average over a certain set of numbers. So you should think of this as the set of matrices which satisfy these, which are triangular, of determinant n, and this B is bounded by D and it's positive. So you have this set of matrices, and now you make an average of your function by just adding over this set. And then the key property is the following, that if you make this averaged sum, then you will end up with a modular form. And there are several ways to prove this, and actually one way is just by knowing what is actually going on. And so we will see in a second that if you apply this Hecky operator to this modular form, then you get this quantity here. And I see some of you taking notes. So the notes are online. So you just follow the link of the of these talks in this conference. And so it's more that you take additional notes that you can say, okay, I was putting this, but actually, at least for this week, I want to give you just the notes as you've seen here. So you just, it suffices to make your comments and to write it down for your memory, but to write down the precise formulas is maybe not necessary. And I decided to give these talks on slides because I can give you more formulas, and you can check them at home. And we can make the exercise challenge, who's finding more typos. And maybe I give a present and we celebrate the one who finds the most. Okay. So we have this explicit formula for the Hecky operators. And out of these explicit formulas, you can get identities that the Hecky operators commute, which is essentially contained in this formula if you view them from the other side. So you really have these identities for these Hecky operators. And okay, what is the idea to prove this? So if you make a substitution of holomorphic substitution of variables in a holomorphic function, then composition of holomorphic function is holomorphic. Therefore, T and F is holomorphic. So the next is we have to study this set we are summing on. And for this, we consider the set of all integer 2 by 2 matrices of determinant n. And now, if we multiply a determinant n matrix with a determinant 1 matrix, the determinant is not changing. But therefore, we have a natural action on this. And now, if we take the classes with respect to this left action, we just get these matrices we wanted to sum over. But now, if we sum over these matrices and apply an element of SL to Z, then because we just put this zeta plus d on the other side of the functional equation, the statement of being modular means that this so-called slash operation on this modular form is invariant. And therefore, it does not change. So we're just changing the set of representatives of this equivalence class, and therefore we will get an object which is, again, modular. Okay, so this is the first statement. I come back to this point later. So the main point is now to show that F is holomorphic. Recall, modular means holomorphic, modular transformation, and holomorphic at infinity. And for this, we have to study the action of these Hecky operators on the Fourier expansion. And so we write down the formula for this Fourier expansion. So it's just we plug in this. And now we use these nice properties that if you sum up roots of unity, then most cases you will get 0, and only a few cases you will get some non-trivial number, which is in this case d. And now if you just resort which d's gives you this non-zero contribution, you just end up with a formula for these new coefficients we had in the slide before. And for this, you have to do twice a variable substitution in order to get these beautiful formulas. And actually, you can use this explicit formula for this new Fourier coefficients after applying the Hecky operator. Again, playing with some identities for roots of unity in order to prove this claimed commutativity of Hecky operators and this recursive property for prime powers. So this can be really deduced just from this explicit formula. And thus we get that the Hecky operators act. And actually from this explicit formula, we can read off that cusp forms are preserved. So we just look what's going on with the zeroth coefficient. But the zeroth coefficient is just a multiplication by some non-zero number of the zeroth coefficient in the Fourier expansion of our F. And if the A0 is 0, then the gamma 0 is 0. And therefore, the action is preserving the cusp forms. Okay. We have now these operators. We have many of them for each integer, so we can make an algebra of them. This is a so-called Hecky algebra. And the remark is we presented here a down-to-earth approach to these Hecky operators. So it's just giving some matrices and they act on this space of modular forms. Yesterday, it was just there. I think you were talking about these double cosets and so on. So there's a nice approach to these Hecky operators just by double cosets, which is maybe found in this book by Shimura. You can find Hecky operators as being in correspondences. I think we've seen also this push forward and pull backs. So this is, for example, in this in Rawley's article in this Cornell Silverman book, which is saying something modular forms and modular curves. So there, the Hecky operators are just defined by means of algebraic. Oops, sorry, I was not following. So in the algebraic, it is here. Then you can define them as being correspondences on lattices. So this is in Serre's course Arithmetic. That is his approach to Hecky operators. And the upshot is that Hecky operators are somehow in the core of the theory of modular forms. And all these very famous results in the last years or decades are somehow related to Hecky operators. For example, the famous theorem of Mazur, that if you have an elliptic curve defined over Q, then there's only a finite list of torsion subgroup. This is relying on the Hecky algebra of the Jacobian of this associated modular curve x0n, and this is the so-called Eisenstein quotient. And also Weil's famous proof of Fermat's last theorem is also about Hecky algebra and deformation and so on. So really, the core of modular forms is in these Hecky operators, and it is really becoming interesting as you put a level on this. But here it's just down-to-earth formulas, and it is just to make you appetite to study some very interesting stuff. Okay, so we have this Hecky algebra here, and now we do some little linear algebra. It's like if you have a finite commutative C algebra, and if this can be embedded into the endomorphism of a finite dimensional vector space, then you will find a simultaneous eigenvector for all of these operators. So it is clear if you have one operator, you will find an eigenvector. It is just due to the case that a complex polynomial does have a root. And therefore you can solve for this root. But now, if you just denote the space, eigenspace for one of these roots by V1, then you can restrict the action of the others on this V1 by this commutativity. And now you exchange the operation, and then you will see, oh, it has to be an eigenvector also again. And therefore, you can go further and further, and at the end, you end up with a simultaneous eigenvector. So this is just simple linear algebra and a little bit complex. That's the fundamental theorem of algebra. This allows you to ask for simultaneous eigenvectors. And so this applies to our setup. You see, we have these very complicated functions, but what do we have? We have just a tiny finite dimensional vector space. It's like if you make linear algebra, you just think of these coordinate vectors, but there can also be functions and they could be modular forms. You have this commutative algebra of Hecky operators and the endomorphisms of this vector space. The linearity is preserved. You can apply this, and therefore it is an honest, reasonable question to ask what are the eigenforms for these Hecky operators, and we call them Eigen Form, and we can even normalize this, which then has a nicer formulas by requiring that the first coefficient is 1. And now the theorem is if we have a modular form which is an eigenform, then we must have that the first coefficient is non-zero, and if in addition it is normalized, then the nth coefficient of the Hecky eigenform equals the eigenvalue of the nth Hecky operator. So it is a strong interrelation between this modular form and the Hecky operators. Okay. The proof is easy. So what do we have? So the coefficient gamma 1 of the formula we've seen before, this is A1, AN. But on the other hand, the gamma 1 is just lambda n times A1 because it's an eigenform, and therefore AN has to be lambda n A1. So if A1 is 0, all AN are 0. And the other point is because the Hecky operator really determines you all the coefficients of your modular form, then if you have two modular forms which belong to the same eigenspace, then they have to be proportional because they only can differ in the first Fourier coefficient, and that's the reason why we take a normalized Hecky eigenform in the sense that we have a canonic representative for this eigenspace. Okay, so we have this, and again, we had seen the this multiplicativity of these Hecky operators and this recursive property. But now we recover this just in the Fourier coefficient of our modular form. So the modular form now must have multiplicative coefficients. And multiplicative in the sense of arithmetic, multiplicative arithmetic function. This means if we have co-prime numbers, then it will be no interference. And if we have prime powers, then there will be an additional formula, and the additional formula is like this. Maybe some remark. I would prefer to say that AP to the n is expressed by the guys before, but traditionally you have to write it in this direction, that you say AP times AP to the n equals to this. And even another way would say, okay, put this on the right-hand side with a 0, and you say 0 equals to this. So then it's completely democratic, and no term has more right than the other. But this is the way people present this. And now we are answering the question I asked for motivation. So which LCs have an Euler product? And the statement is the normalized Hecky eigenform give us LCs with Euler product. And you see the APs determine all these ANs, which is clear by this coprimality. You can reduce to powers of a prime, and then you will find this. Okay. Yep. And what to do? So the first is just general nonsense. So you start with multiplicative functions, and for any multiplicative function, you have a splitting of the Dirichlet L series just in the product of primes times the coefficient that corresponds to prime powers. So this is general nonsense. But so the important thing is that this quantity here is in fact a rational function. And in order to prove that this is a rational function, it is more clear to replace the t, the p to the s by some t, because this is then easier checked as an identity of formal t series. And so what do? You just multiply this to the left hand side. You multiply this to the left hand side, and then you get that it should be 1. And now you just multiply this out, and now you get this democratic ordering of these APs. And the condition was that all these are zero, because let's say because it's Hecke. Okay, so you get these nice properties for Hecke Eigen Form. And now, what is the upshot? So it was a conjecture by Model, and Model proved it, and it was a conjecture by Ramanujan that the Ramanujan, I said it the last talk, that this is called Ramanujan tau function, so that the Ramanujan tau function is a multiplicative function, but now it is almost obvious, because the space of cusp forms of weight 12 is one-dimensional, and the Hecke operators act on this space, and there's only one chance that this must be an eigenfunction, because there's no other modular forms you can put this into. And so it is an eigenfunction, and therefore this Ramanujan tau function has to satisfy multiplicativity properties. And again, this is in the style of the alluded program that modular forms give you identities for free, which are hard to prove by other methods. And again, this coefficient, this Ramanujan tau function, was so hard that Ramanujan could not prove multiplicativity. So it may indicate that it's not trivial. So you need some trick, and the trick was to use Hecke operators. Okay, and you can do some examples. Maybe, yeah. Maybe a general senior advice, somehow, with respect to modular forms, I'm socialized by Don Sagier, and one point is you should make examples. You should make lots of examples, and once you make lots of examples, you understand the pattern, and once you understand the pattern, you can start making proofs. And so if you make examples, if you make experiments, somehow you widen your mathematical spirit, and then you can prove. And therefore, I'd love to have these examples just to indicate that it's a kind of useful benefit to have this property. And for example, if you want to calculate these numbers, then you really see, it's helpful to have this multiplicativity. Maybe when I start talking, this Ramanujan tau is very nice, and also there's a so-called Lemma's conjecture, which saying simply stating that tau p is non-zero, and if tau p is non-zero, then all tau n won't be zero, and it is okay no, sorry. Let's formulate it another way. So it's tested up to very large primes. So it's a primes about is it 20 digits or something like this, or 27 digits. So it's rather big. And the point is, in order to test this, you really need a force of difficult arithmetic geometry. And so to name, so it's Edixhoven, Cuvenius, it is, you know, Anil. It is Robin de Jong, and there's also the other one with the Green's function. What's its name? Brün? I think Brün. Okay, so the point is you can prove this, and it's a kind of semi-theoretical algorithmic proof. So you really work with approximation of Galois representation, and it's very inspiring techniques what they are using. And so they are combining very hardcore computer algebra knowledge by Jean-Marc Couvenius, and also some very hardcore theoretical knowledge of Bas Edixhoven, and also the knowledge of Robin de Jong of Arakelov geometry. And all this together allows them to make an algorithm for which they use the knowledge, I think, of Brüm and also another guy, I forgot his name, on how to implement Green's function very cleverly on a computer numerically. And this allows them to prove this non-vanishing of this number, because the point is if you prove that some integer is bigger than 1/2, then it must be non-zero, because this is essentially the trick. Okay, so again, some little appetites. Coming back to Eisenstein series, the Eisenstein series are also Hecky Eigenforms, but this way we prove it the way backwards by just recognizing that these divisor functions satisfy these nice multiplicative properties. And also we can make the L series. So we define the L series a priori for cusp forms, but we can also make L series for modular forms by just ignoring that there is a constant term. So we just neglect it. And if we make this for the Eisenstein series, then we can get something very interesting. Namely, it's a product of Riemann's zeta function, and the proof is easy. You just write it down, and then you separate this, and then you get this identity here. So also for, yeah? Yeah. Yes, so it's found in a paper by Don Sakier. It's called the ranking Selberg methods for functions which are not of rapid decay. And a particular example are Eisenstein series, something like this, but it can be done in a much, much broader context. And the rough idea is you cleverly subtract the constant term, then you get something that is of rapid, or of, let's say, of rapid decay. And then you make some convolution with some non-holomorphic Eisenstein series, then you prove some analytic continuation, and then you get some very nice Elf functions. And you can reconstruct these thrown away in the constant term of the meromorphic continuation of these modified ranking Selberg convolution. So it's a nice question. This question has been answered by Don Sakier already 25 or 30 years ago. So this is a remark on this. Okay, and again, you can make examples, and you can read this at home. Okay, now we have these Heck operators. We know that there might exist eigenfunctions and how we can find them. And the point is, you can just enforce this by doing calculations. So if you have this space S24, it's two-dimensional. You know a potential basis of this, and then you just make what the German word is an Ansatz. And so you say, okay, what must be satisfied that this function becomes a Hecky Eigenform? So you enforce this, and then you get that this equation must hold. But this is a quadratic equation. You can solve the quadratic equation, and then you see that this must be a Hecky Eigenform. And the motivation for this, if we look at this, then the roots of these polynomials are real numbers. And the general theorem will be that whenever you have an Hecky Eigenform, it will have algebraic coefficients which are in a real number field. It's a totally real number field which also attracts number series. And so the upshot is that there exist Hecky Eigenforms because you just enforce this. You have a finite number of equations you have to solve. When you solve this finite number of equations, you get an Hecky Eigenform. And so there are ones. And the point is, again, linear algebra. If we have a vector space with a Hermitian scalar product, and we have operators that are self-adjoint with respect to this, then we find a basis of eigenvectors. So a priori, we only know there are some eigenvectors, but once we have found a scalar product with the appropriate properties, then we will get a basis of eigenvectors. Okay. There is this scalar product, and it is named after Peterson, and it is given by this formula, and essentially we've seen this in the Ameya. In Ameya's talk, and okay, he did use another notation for this volume form. So I prefer to have write it as a one form. He just wrote a big dz, and but this is the same formula. So what are you doing? You have some invariant integrand, namely this pointwise Peterson norm, and then you make the L2 average of it by integrating it over the whole space, which is here this fundamental domain, and you integrate it by something which we will see in a second, which is invariant. And therefore you get some number, And in order to check that this is a positive definite Hermitian scalar product, we have to check 4 points. So 3 of them are quite obvious because they just about complex conjugation. And so it's a positive definite. Okay. It is Hermitian, which is also clear. And obviously it's bilinear, which is also not so difficult. So the more difficult point is to show that it's well defined. And let's see, in time, I promise to be quick. So I start and then I will skip parts of the proof. The pedagogically best way to start this lecture would be to prove with you all these nice identities, to say, okay, if we, for example, have the imaginary part, then it transforms like this with respect to the action of SL2Z. And if we make this together, then we see that this quantity is invariant. I think this minus is okay, because then the plus and the minus is okay, but I think there is a 2 missing. The 2 is missing because otherwise this won't be invariant, because we have the absolute value to the square. And I forgot the square. But then it turns out to be invariant, and I will be quick, maybe you find more typos. And the good thing is that the formulas are in essence correct. Maybe I mistyped it. And another formula you need to know is how the D is changing. And essentially, the D is a modular form of weight minus 2. This is something you have to remember. And the formula maybe is not so important, because once you know this, the D is a modular form of weight minus 2, then you just know what to do. And again, you make this calculation, and at some points you need to make some simplification that AD minus BC equals 1, and then you get out these. But again, using this formula for the imaginary part, you see that this dx dy over y squared is invariant under this group. Okay, therefore you get that the integrand is well defined. Okay, and now I'm starting to be quick. What is the point? So the point is you make this multiplication. At some point, you have to justify that the integral exists. And you do this by splitting the fundamental domain in 2 areas. You have something below, and you have something upstairs. For the thing below, everything is fine because it's compact and you work with nice function, but you have to study what's going on here. And in particular, if you go to I infinity, but here, if you go to I infinity, you're using that you have cusp forms, and cusp forms are rapidly decaying. And so you will end up with something that is well defined. So you get something that is smaller than infinite, and this will be then prove the well-definedness of this Peterson scalar product. And what is the next theorem? And for this, I will be honest. This is a long and nasty calculations, and even people are not satisfied with every presentation in every book. So, for example, if you go to the book of Knapp on elliptic curves, then you have to take a deep breath and to accept this, what he's writing. And so, in essence, it is okay, but you have really to go through this double cosets calculation, and it's a real mess. It is doable, and it was done 100 years ago, and so it's now high technique mathematics, and we don't do this here. But the important thing is the Hecky operators are self-adjoint with respect to this Peterson scalar product, and the consequence is that we have an orthonormal basis given by Hecky Eigenforms. So this is the second statement I wanted to show you in the course. So you really have this eigenspace by Hecky Eigenforms. And the other point is that the Hecky Eigenforms have real algebraic numbers as coefficients, as if we set the first coefficient to be 1. And so it's a nice supply for totally real number fields. So totally real number fields have application in arithmetic and so on. And so this gives you a nice supply for these totally real number fields. Okay, so you have this very important result that we have this orthonormal basis of modular forms given by Hecky Eigenforms. This has some practical implication because we can reformulate it in the sense that we have a bilinear and non-degenerate pairing between the Hecky algebra and the modular forms, just sending a modular form to its first coefficient. And this is easy to see that this is non-degenerate, and therefore we get some map from the modular forms to the homomorphisms of this Hecky algebra to see. But if we make it the different way around, so if we have a homomorphism from the Hecky algebra to the complex numbers, then we can make a modular form. And so if you want to do experiments, then you can, for example, use Sage or Pari, and they give you modular forms. And in order to efficiently calculate them, they use the action of Hecky operators on the so-called modular symbols. And this can be programmed very efficiently. And this allows you to calculate the coefficient of these modular forms. So you can use this Hecky algebra algorithmically to produce modular forms. And this is due to this non-degenerate pairing. And you can get a basis for the space of modular forms because, you know, Hecky Eigenforms give you a basis to the space of modular forms. So this is some practical implication. And so this is nice. And also, I still have 5 minutes or something like that. So for the purpose of the talk for tomorrow, it is nice to know that we have these ranking Selbert methods. And the way is what in more technical term is called parabolic induction. So if we have these Eisenstein series, then this was given by just summing over the all non-zero vectors. Oops, sorry. Over all non-zero vectors in this lattice spanned by tau. But you see, these vectors may be just scalar multiples. And therefore, we take out the scalar multiple and bring it into the front. So it suffices to know what is this sum just for the coprime integers, because we get all the others by multiplying with some factor. So therefore, we can take this out, and again, we see this zeta k coming into the front here. And so it is the sum over all coprime integers. Okay, but now we have this Euclid lemma telling you if you have two co-prime numbers, you will find other numbers that sum up to 1. How you call this? You use this extended Euclid algorithm, or in the more fancy term that two co-prime numbers generate an ideal, generate the full ring. So it's a it's a principal ideal generated by 1. And you get the generator for this ideal by means of this Euclid algorithm. Anyhow, if you have these co-prime numbers, then you will find some A, B, C, D such that you get this matrix here. But now if you have any of these matrices, then you can translate this by this matrix T, and you get another solution. So you just make this CD, and I hope that's, yeah, maybe I made a mistake yesterday, but anyhow, you get another solution. So you get lots of solutions. But if you play this game, it is not saying that this sum here can be expressed just as the classes of these SL2Z modulo this subgroup generated by T. And the keyword is that this is a so-called parabolic subgroup. And so what are you doing? So you have something that is not changing, and then you're summing up over all these classes. Okay, and now we will use this for the so-called Rankin-Selberg unfolding. So if we have two cusp forms, or if we have a modular form, if we have a cusp form and a modular form, then we can also calculate the Peterson scalar product. So we can extend this from the space of two cusp forms to the space of one cusp form, one modular form. And now we can calculate this. So we take a cusp form, and a cusp form, any modular form, and some Eisenstein series in such a way that the weight is fine. And then the point is you really can calculate this Peterson scalar product, and you get this nice convolution L series. I think that's how you call this. Okay, and so what is the trick to do this? So the point is you have this integral. Now for this integrand you apply this identity for the Eisenstein series, and now you can really rewrite this as a sum over these equivalence classes of the group modulo its parabolic subgroup. And then on the next slide we just put this expression and interchange the sum and the others. And so what does this mean? So we have this fundamental domain, but now we have this and this and this and so on. And actually what we end up is just the strip. So we are doing an unfolding. So all these translates come up, and therefore we end up with an integral here. And this is now easy because integrate from 0 to 1 is killing you all these frequencies. So only the constant term of this scalar product will remain. And so we end up with one of these easy integrals we've seen before. So it gives us just an n to the minus k. And so we end up with this formula for this Rankin-Selberg transform. So what we've seen today is LCS of modular forms. Particularly nice LCS of modular forms are those of Hecky series. Then we have the Peterson scalar product. And the Peterson scalar product allows us to prove the existence of an Hecky eigenbasis. And using this Rankin-Selberg unfolding, we were able to calculate some of these Peterson scalar products. And in particular, if we apply this now to Hecky Eigenforms, then we can even go further. So if we apply these to this kind of Peterson scalar product, we get a formula like this. And this can be even further simplified so that we get rid of this additional multiple divisor sum. And so we get some identity that will be used tomorrow. Okay, so thank you for your patience, and I'm finished.